Okay, last section of the chapter, 12.5. There's your homework. All right, this is a pretty straightforward class. We're going to get basically one theorem and do a couple problems. It's not too challenging at all. Definitely needs to take a little bit of time to get to the answer, but once we get there, it's pretty straightforward what the results are. All right, so we're going to start off with the definition for your book of truth. Let's see, we've had similar shapes before. We apply that to, or similar polygons. We've applied that for 2 dimensions. When we switch to 3 dimensions, we say similar solids. So these are the 3-dimensional shapes that have the same shape, but just a different size. So you have a pyramid or a cylinder, and you just increase that by a scale factor of some sort. All right. And it's just like similar figures as I just stated before. So let's gather some data. This is a really crummy proof, but it's the proof that we're going to use. So I've got 2 examples here, one with 2 right cylinders and 2, the second one there, I've got 2 regular square pyramids. All right, so let's see what we got going on here. I'm going to have a little table here. So I'm going to use these shapes right here. I'll show them again on the slide here. But these 2 shapes right here, 2 different examples. And I've got a column that's labeled cylinder 1 and cylinder 2, and a second column labeled pyramid 1 and pyramid 2. So we'll do each one of these columns one at a time. So we'll do the cylinders first. First off, let's figure out the scale factor. Remember the scale factor, if 2 shapes are similar, or in this case, 2 solids are similar, then we can pick any 2 sides that are corresponding, and we can write a scale factor. So I'll just go from 1 to 2, from big shape to little shape, and just pick 2 of the corresponding sides. I could pick the radii, or I could pick the height. I'll pick the height. If you're doing this yourself, pick the one with the smaller numbers. It's easier. So we get 12 to 8. 12 is the height of the big one. 8 is the height of the small one. Reduce that fraction, we get 3/2. And notice that would be the same as if we had picked 6 and 4. That would also reduce to 3/2. So my scale factor is 3 to 2. All right, next row says, give me a ratio of the base perimeter. All right, so the perimeter, well, it's a cylinder, so the base is a circle. So the perimeter would be the circumference, and the circumference is 2 pi r. And let's see, once again, I'll do perimeter or shape 1 to shape 2. So let's see, 2 pi r, the radius of the big one is 6. So 2 times pi times 6. And on the small one, 2 times pi times 4. Do a bunch of reducing here. The 2's would cancel. The pi's would cancel, and I'd be left with 6 over. Hey, that's 3/2 as well. Coincidence? Well, let's see. Let's do lateral area. Remember the lateral area of a cylinder, we'd have to look through our book of truth. Let's see. That was if we cut the side off and we lay it flat, we got a rectangle, which would be base times height. But the base would be the perimeter of the circle, and the perimeter of the circle is 2 pi r. So remember, this is that one that was 2 pi r h. Okay, so let's do that ratio. So once again, the big one to the small one, 2 pi r h. Radius is 6, height is 12. On the small one, radius is 4, the height is 8. The 2 and the pi's would cancel. 6 times 12 is 72, and 4 times 8 is 32. We'll reduce that. Let's see, what goes into both? I think 16? No, not 16. What goes into, 16. And that would reduce to 9, 4, no, 8. 8 goes into, 16 doesn't go into it. 8 goes into it. 8 goes into 32 4 times. 8 goes into 72 9 times. Well, that's not 3/2, but check this out. 9 can be written as 3 squared, and 4 can be written as 2 squared. So I do get a 3/2, but it's squared. Very suspicious. Well, lateral area, remember the units would be in square units. So is it surprising that the lateral area of these 2 similar solids is the scale factor squared? All right, that's not proof, but that's strong evidence. If you take that same concept and you think about the volume, well, my guess, since volume is cubic units, the answer should be 3 cubed over 2 cubed. Well, let's see if that's true or not. It's a guess. Let's see, formula for volume of a cylinder is base area times the height, or pi r squared, that's the base, so it's a circle, times the height. So pi r squared h. Let's see, on the big cylinder, r is 6 and h is 12. And on the small one, r is 4 and h is 8. Well, the pi's cancel. 6 squared is 36, 4 squared is 16, and 36 times 12 is 432, and 16 times 8 is 128. That's not recognizable, but what goes into both of those numbers? Let's see, is that a 41? Is that the number? I'm grabbing my calculator right here. Is it? No, it's not 41. 128 divided by 16. 16 goes into, that's the 6. I knew there was a 16 here. 16 goes into 128 8 times, and 16 goes into 132 27 times. Well, that doesn't look like 3 and a 2, but 27 can be written as 3 times 3 times 3, and 8 can be written as 2 times 2 times 2. In other words, 27 over 8 could be written as 3 cubed over 2 cubed, and that's what we suspected. All right. Now, even before I do it to my second set of shapes, these ones right here, you can make a prediction that if I can find the scale factor, then I can complete that column right there just by following the previous pattern, previous column's pattern. The base area perimeter ratio should be the same as the scale factor. The lateral area should be the scale factor squared, and the volume should be the volume cubed. All right, so let's see, or the scale factor cubed, I'm sorry. So let's see if that's true. So let's see, we got to do the scale factor, pick any two corresponding sides. I'm going to pick the slant height. The slant height is on the big one 10 and 5 on the small one. 10 over 5 is a 2, or 2 over 1. So that's my scale factor. Now, if I follow this pattern, then my base perimeter ratio should be 2 to 1 as well too, but we'll go ahead and do the math to confirm that. So let's see, the base perimeter, well, the perimeter is that, well, it's a regular square pyramid, so there's a square on the bottom. So on the big one, that would be 12 times 4, because there's 4 sides. 12 plus 12 plus 12 plus 12, or 12 times 4 is 48. And on the smaller one, a side length is 6. 6 times 4 is 24. And if we do reduce that fraction, what goes into 24 and 48? Well, 24 does. We get 2 over 1, as we thought we would get. And so without even doing the rest of the math, the final two answers should be 2 over 1 squared and 2 over 1 cubed. We're just going to verify that, and then that's where our theorem is going to come from. So the lateral error, remember, from our book of truth was PL over 2, P being the perimeter, L being the slant height. So let's see, on the big pyramid, the perimeter is, well, 48 again, and the slant height is 10. So we're going to get 480 over 2. And on the bottom one, let's see, the perimeter is 6 times 4 is 24. The slant height is 5 over 2, because remember, it's PL over 2. If I do a copy dot flip on this, if I do a copy dot flip on this right here, I would get, after the 2's cancel out, and I did 48 times 10, I would get 480. 24 times 5, we would get what, 120, and then reduce that by 60 goes into both of those, and then reduce that again, we get 4 over 1. What's up? Where ones? Yeah. So we get 4 over 1, but 4 over 1 isn't squared, but you could write 4 as 2 squared, and you can write 1 as 1 squared. So we get 2 squared over 1 squared, and we got what we thought we were going to get. So without doing the math, we can just predict that it's going to be 2 cubed over 1 cubed, or 8 over 1. And here we go. Volume, remember, is BH, capital BH, divided by 3. Remember, it's that pyramid. Take 3 regular pyramids, it makes a cube. So 1 pyramid would be a cube divided by 3, and that was B, capital BH. Divide that by 3, you get 1 pyramid. All right, so the base area of the big one would be 12 times 12, because it's a square. The height is 8. Right, so you get 12 squared times h divided by 3, and on the small one, let's see, the base would be 6 squared, because the side is 6. The height is 4, divided by 3. Do a copy dot flip, the 3's would cancel, And on the bottom, you get 6 squared times 6 squared times 4. On the top, you'd get 144 times 8. Do a whole bunch of reducing here, and we get 8 over 1. All right, and 8, remember, is 2 cubed, and 1 can be written as 1 cubed. And we got exactly what we suspected. And with that weak evidence, and that's evidence for these two specific shapes, two regular pyramids and two right cylinders, it's definitely true for those. This is why this one's weak proof, but we're going to extend this to all similar solids. So here's what you need to write down in your book of truth, and this is the only thing of today's lesson, is that if you know the scale factor of two similar solids, and if that scale factor is A to B, well, then the perimeters of those two similar solids will also be A to B. That's statement number one. Statement number two is if we do anything with their areas, for instance, the area of their bases or their lateral areas or even their total areas, then that ratio will be A squared over B squared, convenient. And lastly, the volume will be A cubed over B cubed. All right, so the complexity of this is not very complex. You simply need to find out what is the ratio of two of the corresponding sides, and then you can figure out everything there is to know about perimeter, area, and volume. All right, probably need to see one example of this. So here's your one example. So you will be told that you have similar solids. So I am told right here that these two solids, they're both triangular prisms. They're not pyramids, triangular prisms, and we're told they're similar. And it says calculate the ratio of their perimeters, their lateral areas, and their volumes. And if we use that previous theorem, which there it is right there, you're going to see how quickly this is done. So if we do their perimeters, well, the perimeters are just the scale factor. And their scale factor is, well, it depends whether you want to go from small to big or big to small. I guess I'm going to go from small to big, right? So if I go from small to big, I pick two corresponding sides, any two corresponding sides. Well, they only gave me two sides here, 6 and 10. So I write that as a fraction, and I reduce it, and there's your scale factor. So there's the answer to question number one there, the ratio of the corresponding perimeters. Question number two is the ratio of their lateral areas and total areas and base areas. Well, it's 3 to 5, but squared. In other words, it would be 3 squared over 5 squared, which would be 9 over 25. That was easy. And the last one is easy as well, too. If we want to know the ratio of their volumes, we take the scale factor, 3 over 5, and we cube it this time. 3 times 3 times 3 is 27, and 5 times 5 times 5 is 125. And believe it or not, that's how homework is done. And it is that simple. The only difference for homework is sometimes they will give you the ratio of areas, or they will give you the ratio of volumes. So can you go in the opposite direction if I give you those values? If I give you this one right here, can you go back to the scale factor? And the answer is yes. If you're given volume, then we simply need to take the cube root of the top and the bottom. The cube root of 27 is 3, and the cube root of 125 is 5. If they give me the ratio of the areas, then I'm just taking the square root of the top and the bottom. The square root of 9 is 3, and the square root of 25 is 5. So regardless whether they give me two of the corresponding sides or they give me the ratio of the area or the volume, you can get back to scale factor. If they give you scale factor, you certainly can get to the ratio of any of the areas or the volumes by either squaring or cubing the scale factor. And believe it or not, that's the whole darn class. So this particular chapter ends on a nice, easy, this homework will not be too challenging. But if you do run into a problem, let me know. I'll just show you the homework. Yeah, there'll be a table in here, right? It's not that big of a deal. I'll do a couple of these. These are not the ones for homework, but these are the classroom exercises. If they give us the scale factor right here, then anything that says area, this says area and this says area, will be the scale factor squared. In other words, this would be 9 to 16. Anywhere where it says area 9 to 16. That was supposed to be a colon right here. That was horrible. Anywhere where it says volume, then it's going to be that number cubed. So let's see, 3 cubed would be 27, and 4 cubed would be 64. So 27 to 64. And anything that doesn't say area or volume, and then it's just the scale factor. So this would be 3 to 4, and this would be 3 to 4. And that's how it's done. If they give me the volumes, then I'm simply taking the cube root of that to get to the scale factor. The cube root of 8 is 2, and the cube root of 125 is 5. We just literally just did that one. Okay, that is how those tables are done. And I think that'll do it for today. I'll just show you the homework and we'll call it a day. And there you go. There's your homework. Good luck with it. But if you do run into a problem, don't hesitate to ask me a question. We'll follow this up with tomorrow will be, or the next class will be practice test. So I'll give you a practice test. And as always, when you're ready, just ask for the test and we'll go from there. All right. See you later.